And I'm back again. Are you as excited as I am? I can see the excitement on your face. Okay. Oh, I guess before we get going, I just had a funny thought. I can draw a picture of myself, a cartoon. Oh, not if I don't turn on the style on the pen. Okay, let's see. I made this up when I was younger, so this looks more like the younger version of me. There we go. Yes, I'm a ham. But it's almost Thanksgiving. Okay. Sounded like the count right there, right? Okay. Sorry. I'll start doing math now. Okay, so we got a new definition. This set NZ. If you get into cryptography or you want to do, you use this set here. NZ. Okay. NZ is really just multiples. Okay, so I'll list some of the elements of 2Z. Okay, so before I do that, 2Z is 2k such that k is an integer. 2 times k such that k is an integer. Okay. So some integers, let's see, so 2, so you have, okay, right. So, remember, okay, so let's see, we had, let's do like dot, let's see, -6, -4, -2, 0, 2, 4, 6, dot. So just the evens. It's really just the evens. Okay. In a second, I'm going to show you a proof that 2z is a subset of z. Okay, so let's go on to B. Just think about what we're trying to prove here when we do this. Remember that, okay, let me go back up here. Oh, that's not up there. Remember that saying that, oh yeah, I just have it, I wrote it right there. That this actually means this. It's a conditional, a quantified conditional. Okay, so what we want to prove that this conditional is true, right? So we're going to prove that this is true. To prove this is true, what we really have to do is just eliminate that row. Okay, so all right, so now think about this, right? So 2 possibilities here, right? 2 possibilities. X is in 2z, so x is even, or x is not in 2z. X is not even. Either x is even or x is not even, right? Another way to say x is not even is to say that x in 2z is false, has a false truth value. Right? Okay, so let me write that. Oops, my bad. Okay, so what? So if we have this situation where x in 2z is false, then that puts us in one of these two situations. And we always get true in those situations, right? Okay, so the proposition is true if x is not in 2z. That means the contract is void. Okay, so when's the so the only time when we're not in this situation, so the only time that we have the possibility of getting false is here, right? That's in one of the. That's when this thing is true, right? So to prove it, we really only have to assume. We can just assume that x is in 2z. Okay, so I'll do the proof now. All right, so what I just basically said was like this is why, what I'm basically saying right now is this is, or what I was saying here in part B, is just that this is why we can assume x is in 2z. Because if x, that's why we can assume this part. We assume that x is in 2z, and then we show that x is in z. Now, why can we assume that x is in 2z? Well, because if x is not in 2z, right, then we get true anyway by our definition of if-then. So we may as well assume it. Okay. I want some more room here. So now we'll prove it. Proof. Okay. Now remember, 2z is the set of all 2k such that k is in z. So if x is in there, right, if x is in this set, right, so then that means that x equals 2k. If x is in 2z, that means that x is, so x equals 2k for some k, some integer k. But instead of saying integer k, I can just write k and z now. All right, let me write this as for some integer k, because I think that'll be more clear. For some integer k. Now, since 2 is an integer and k is an integer, 2k, which equals x, is an integer. So x is in z, and so look what we proved, right? We assumed that. And we showed that. So we showed true implies true, therefore the proposition is true. Oops. Okay. There's that.